Hello everyone. Well, this week we're going to look at building our first predictive model in R. And so what I'm going to do is I'm going to run through a couple of slides that sort of introduces the concept of the linear model function that we're going to use in R, but also give you some background information about what we're really doing when we're using the linear modeling function. And in this particular case, what we're doing when we're actually using linear regression. We'll talk about that, and we'll also talk about the calculation of error. When we make predictions based on past data, we are hopefully going to be as close as possible to the actual values, but sometimes we're going to be off. In fact, most times we're going to be off. And sometimes that error, or that amount that we're off, which is known as error, will be fairly large. It's going to depend on the quality of our model and the data set that we feed into the model. So let's go ahead and talk about this now. Let's go back a little bit and do kind of a recap. I had talked to you a little bit earlier in one of the other modules about supervised versus unsupervised learning. And supervised learning I'm going to talk about mostly here because the linear modeling function in R, or linear modeling at all, is a supervised model. Unsupervised learning I'll talk a little bit at the end here. In supervised learning, what we're doing is we're taking past data that we know the relationships between variables, data that we've had, data that have been processed, whatever, past data, and we're trying to determine what we can learn from that past data. When we learn something from that past data, we can then apply it to future data, and that is where we base our predictions. So if we have two variables that we know are related in past data sets, we can determine the extent to which those two variables are related, and then when we know that, we can apply that relationship to future data where we might only have one of those two variables so that we can predict the second one. There's a kind of a formulaic process that we use when we do this. And the first part is to take your data set, and typically you'll divide your data set up into two chunks. The first chunk will be the majority of your data set, and that's called training data. And it's called training data because it's the data that you use to train your model. So remember, when we're looking at the two variables in past data, we want to determine the relationship, the numeric values of the relationship between those two variables. Then we build that into our predictive model. That's how we're training our model, is we're going back and using the training data. So that, again, makes up the majority of the data that we'll use, the majority of our past data. The remainder of our past data, or most of the remainder of our past data, will be what we call validation data. Once we build our model, we want to validate our model. So we use the training data to actually build the model, and then we go ahead and apply that model to the validation data, and we make sure that everything looks okay, or that it looks acceptable, or that our level of error is not very high, meaning that our model is fairly accurate. So you'll often see a data set in a supervised learning situation. You'll often see a data set that is divided between training data and validation data. The third kind of data that we might have could be a similar data set, but it comes from a different source or a different time. It's not used to build or validate the model. It's different enough from the model that we want to be able to test it out and make sure that the model still applies. And the reason why we do that is that if we have one data set that is, maybe it's 10,000 records, and we use the first 6,000 of those records to train the model, and then we use the other 4,000 of those records to validate the model, they all still came from the same data source or same data file. What if there's some anomaly in that data file that caused the model to not be as accurate as it could be for different data files? So that's where we might go with a test data set. Looks like the validation and training data, but it just came from a different source or a different file, and now we can get a better idea of how much error is built into our model when we're using it for something that wasn't used to build it. Unsupervised learning does not use past data. Unsupervised learning uses the data that is at hand. And so in a situation where you might be looking at 10,000 records and you want to apply a clustering process to those 10,000 records to divide them into maybe 2, 3, 4, 5, however many customer segments based on customer behavior, we're not going to look at past data when we do that. We're only going to look at the 10,000 records that we've dropped into the clustering process to do that. Classification is another model, a statistical process that we would use to identify which classes a record belongs to based on certain parameters. It also is an unsupervised model. But today we're only going to talk about supervised models. All right, let's talk a little bit more about the training data. So with the training data, what we're going to do is we're going to take a look at what has happened in the past. And in particular, we want to look at the relationship between variables in the past. What has been the relationship between customer foot traffic through a store and the weekly sales numbers that a store is able to predict? So is there a relationship there? Well, we can check that with correlation, right? But we can also look at the actual value of that relationship. We have two parameters that the linear model is going to give us that actually allows us to really quantify what that relationship is. And so that's when we build that linear model, because foot traffic through the store would be our input, weekly sales would be our output. And so once we know the actual numeric link of those two fields based on past data, we can then predict, when we only have foot traffic through the store, we can predict what likely sales are going to be. One thing to think about with building a model is how much data do we actually have? So if we only have a small amount of data, then we're only able to make a small amount of predictions based on a really limited view of what the relationship between the variables are. So the more data, the better. And we may get to a point where we're getting diminishing returns because the model doesn't get that much better refined when you add more data. But we still would like to have a better set of data, bigger set of data. By understanding the relationship between one variable and another in past data sets, we can predict how similar data sets will behave in the future. We've talked about that already in this presentation. So can we build a model that takes input variables and outputs predictions? We can, and we're going to. And here's another example. This is the example on the next slide is one that I came up with, sales for the year and Christmas sales. So here's our example. Each year we track sales per customer from January to November 30th. So for the first 11 months of the year, we track customer sales. We want to know, is that a good number or a good predictor for how much a customer will spend at Christmas time? So what we would do is we'd go back to past data, maybe the past 5 years worth of data, and we'd look at the customers that we have, and we would compare how much they spent in the first 11 months to how much they spent at Christmas time. And that would allow us to build a relationship, to understand, or build a model basically, that says if a customer spent X dollars in the first 11 months of the year, they are likely to spend Y dollars in the month of December. So when we're able to do that, then we can identify those that are going to be larger spenders. They're likely to be bigger spenders in December, or those that are going to be lower spenders in December. And how would we market to them? Would we market to them at all? So that's really how kind of practically useful a regression model, a predictive regression model can be. There are mathematical formulas that help us with this, and we'll look at those. And then linear regression, or LM in R, is the function that we will use to build our first linear model. Let's talk more about linear regression as a predictor. So what is the linear relationship between variable A and variable B? When we think linear, we think that when variable A increases or decreases, variable B has a very predictive behavior in relation to variable A. And that's why it's linear. We can pretty much say that given any amount of A, we can predict B because the linear relationship allows us to do that. We're going to change our terminology here, though. We're going to, instead of talking about variable A or variable B or sales or this, that, or the other, we're going to talk about input variable X and output variable Y. The reason for that is that most models that look at things like linear regression are going to look at X as the input and Y as the output. When we know X and we've built a model, we can output Y from that model. X is typically the input variable or the independent variable. And the independent variable, what that really means is it means that it's the one that is having an impact on the dependent variable or the output. And that makes sense in our case because we're using X to predict Y. So when we have things like X, which could be our sales for the first 11 months of the year, we know that the dependent variable, Y, is going to change relative to X based on our linear model. But we want to know to what degree. So we're going to look at linear regression in this equation. And then Y is our output. Y is our predicted or output variable. And we were able to calculate that because when we run the LM function in R or in other statistical software, it will give us two values. And the first value it will give us is the intercept value, and the second value it will give us is the slope value. Let's talk about slope first. Slope is the amount of change in Y for each unit change in X. And so what that basically means is that when X goes from 10 to 11, it will change in a predictable and linear manner, and that is defined by slope. So that's why you see the slope times X. The intercept is just as it says. The intercept is the place where our trend line, which we're drawing, our trend line will cross the vertical axis. So it's basically our starting point. It's our starting point on the vertical axis, and then as each unit of x goes up, as we move towards the right in our graph, we will increase by slope. We'll talk more about that as we go through the example. So I've sort of already defined slope and intercept. For every increase in the variable x, y increases by a fixed amount, and that's why it's linear. All right, let's take a look at a visual example. What we've done here is I've run a plot, just a basic plot of scatter plot, I guess, of two variables, and they're two parts of a flower actually, and petal length and sepal length, to see if there is a correlation between them. And so this is from an old data set, somebody went and measured petals on flowers and other parts of flowers and determined that, when the petal's bigger, the other parts are bigger as well. It seems pretty intuitive, and you can see it actually from the data. The data are pretty positively correlated. They follow a nice vertical line, diagonal line, and so you can see kind of the relationship there. So we see the relationship. Is it strong enough? What can we do with that relationship? Visually, we can see it. And is there enough data there for us to be able to actually build a regression model? So what we would do in this case is we would take this first variable, this petal length, and we would say, all right, we're going to use that as the independent variable. And from that, we're going to be able to predict what the sepal length is going to be. The reason why we can do that is because we look at all of this data here and we say, okay, what has the relationship been between each data point, between the petal and the sepal length on each data point? So we can then we build our model, and then we use each of these data points to predict what that output's going to be. Now, we'll take a look at this in a little more detail on the next slide. Yes, there it is. Okay, so we've run a linear model, and remember I said the linear model will give you two things. It will give you the intercept and it will give you the slope. Okay, I told you that the intercept is the point where our trend line, and I'll talk a little bit about the trend line in just a minute, where our trend line intersects or intercepts with the vertical axis. So in this case, 4.31. If we assume that this is our vertical axis, that's about right. Our slope is the amount of increase each time x increases by 1 unit. So x being our petal length, that's our input. Remember, input is petal, our output is sepal. So each time it goes up by 1, we get some amount of increase in the value of the sepal length, right? These two values were calculated by looking at all of the past data. So the past data looked at all the past data, we did all the relationships, and we came up with an intercept of 4.31 and a slope of 0.41. Okay, what's this trend line? How do we know what that trend line is? Well, really what we're doing is we're creating a line that is based on the least amount of error and the lowest squares. It's least squares, basically. And I'm not going to get into the whole process there, but basically what that trend line is if you were to draw a line that came as close as possible to every single data point in your set, you could be drawing lines forever. You draw a line, you measure every single data point, and then you add up all the error, and then you determine how close was that line. If you draw a horizontal line, obviously that's not going to be very good. And if you draw a vertical line, obviously that's not going to be very good either. But if you draw a diagonal line, you can monkey around with this and adjust it and stuff and try to get as close as possible. Or you can use the terrific, great software we have nowadays, things like R or even Excel does trend lines very well, and several other packages will do them very well. But what this basically is this line, it's your regression line, and it's the line that is as close as possible to every single data point. Now, it doesn't look like it's very close to some of these data points, but if we were to move it closer to these data points, it would be further from these data points. So we have to basically split the difference and get as close as possible. And that's really what regression is doing, is it's going through and it's saying, okay, if I were to look at all these data points and I want to determine a line that is as close as possible to every single data point in the set, I'm going to go ahead and draw that, and then I'm going to calculate what the intercept is. Where does it intercept the vertical axis, and what is the slope? How much does it rise over run for each of these data points as we go? That's where those come from. Those values come from that particular drawing of that line that is as close as possible to every single data point. Here's another example, kind of an example in the, sort of the statistics literature, cricket chirps and temperature. A man by the name of Dolbear found that when the temperature goes up, crickets chirp more. And it was such a predictable amount that he was able to actually use cricket chirps to determine what the temperature was. So it was pretty fixed and it was a pretty predictable amount. and you could use cricket chirps, as a thermometer, but it has errors. All models have errors. What is error? Error, okay, so let's use our example of cricket chirps. We have an input of X cricket chirps. We calculate a slope and intercept. That leads us to a theoretical Y, or a predicted Y, based on past data. But we might also have the actual Y, the actual value, and we could use Z as a variable, but sometimes they just use kind of a variant of Y. You have a Y hat and a Y, one's predicted, one's actual. And what you're really doing is you're looking at, okay, what's the difference between our predicted model and our predicted value and our actual value? And we take that difference, and that becomes our error. And error is the term that is used for whenever a model is off from the actual. And so the best models have the lowest errors. And that's great. And we might take more data, and we might train our model a bit better so that we can reduce the error. We might take more variables and put more variables into our linear model, more input variables, I should say, and that can reduce our error. But the goal is to get as close as possible to an accurate prediction. Have we already seen that the regression line, when you draw the regression line to calculate your slope and intercept, that's the one that has the lowest cumulative error for all of the data points that are in your data set? The quality prediction is dependent on the size of the error, and error is a factor of the quality and size of your initial data set. So small data set's going to yield probably a lot less, or a lot more variability and a lot more error. A larger data set is probably going to be better. Let's look at what we're really talking about when we're talking about error. So we're back to our petal and sepal length, and we've got our linear line here. Remember our intercept was, I think, 4.31, and our slope was 0.41. So this was an actual value, and this actual value was, something that we measured. We had it in our data set. This is our line, though, and so we see that this value is actually quite a ways away from our line. This distance from the actual value to the predicted value is going to be our error, and that's a pretty big error for that particular measurement. But when you get up here, you see that this is almost actually right on the regression line, so it has a very small error. And what we do in order to be able to sort of assess the quality of the model that we've created is we look at every measurement of error, and we add them all up, and we do various different calculations with them. We'll just basically subtract the actual from the predicted. We'll square those values. We'll add them up, or we'll take the mean, or we'll do some method, whatever method is appropriate. But it will give us a numeric value of the overall error. I'm just going to have you do something that's pretty brute force, and I'm going to have you just add up all the errors in the model when you get into R. But that's basically how we assess how accurate the model is. And here's a little bit more about cumulative error. So we calculate the sum of the errors for all the data points. We place the regression line so that the sum is as small as possible. We already know that. We already know that the regression line is going to be the one that yields the smallest errors possible. That is our best fit and our best prediction. There are many different ways to do this, but they can help us understand the quality of our model. So like I said, there's basically 5 different ways to do this. And if we look at these, and we can talk about this actually either next week or more later, but assume that these are our predicted values. We have 4.5, 5.5, 4.2, 3.9, and 5.3. Our actual measurements were 4.3, so we had a difference of 0.2 here. 5.8, difference of 0.3, but it's negative. It's in the negative direction. So then we have 4.2, that's spot on. We have 4.8, which was quite a ways away from the actual value, or the predicted value, I'm sorry, and so that's a negative 0.9. And then our actual measurement is 5.3, and our predicted measurement is 5.3, actual measurement is 5.1 for a difference of 0.2. If you get a list of those, maybe it's 100 or 5,000 or 10,000 long, you can add them all up, or you can square them to get rid of the negatives and add all those up, or you can square them to get rid of the negatives and add them all up and then divide by the number of rows that you have. There's just different ways of being able to calculate this, but it's important to understand that error does play a role in letting us know how good our model is. All right, we're back to looking at our slope and our intercept. We have 106 data points here. That's not a lot of data points to build a model on, but we did it anyway. Remember, we said that our intercept is 4.31 and our slope is 0.41. So this gave us the best fitting line that comes as closest to all data points, and gives us the smallest sum of the errors. Okay, these two things are essentially the same, right? Gives us the best fitting line that comes closest to all data points is going to yield us the smallest sum of the errors and the most accurate model. Okay, we're going to go back to the Boston housing data set, and we're going to take a look at a couple of fields, some relationships between fields. So what we're going to look at is that some of the houses in some of these neighborhoods are really old, and some of the neighborhoods just generally are old. And the older houses have higher levels of nitric oxide in the soil around the house. So can the age be used as a predictor for the level of nitric oxide? Do we have enough of a relationship and enough data in our data set to be able to build a relationship between the average age of the houses in the neighborhood and the level of nitric oxide that's in the soil? So we're going to take a look at that, and we're actually going to do that work in R. So I'm going to cut over to R here in a second. Let's see. Start of R. I'm not using RStudio, I'm using regular R, so if you use RStudio, you can adapt this. I'm going to go ahead and I'm going to load a file. Now I've given you access to this file. It's called Nox.R, and I'm going to go to, there it is. I've got Nox.2 because I got two of them. But I'm going to go ahead and open that up. So you saw what I did there. I did File, Open Script, and then I found my script. And here's my script, and I'm going to pop it over here so that it just looks like it's in another quadrant. All right, it's a fairly simple script. Let's just run through it real quick so we can see what it does. We're going to load up the housing file, which you already have, but if you don't have it, it's in the resources section of this module. You're going to go ahead and import using read CSV. It's a CSV file. Use read CSV, bostonhousing.csv, and then you can pop that into a data frame called housing.df. As I've shown you already, there are various ways to do this. You could do the file.choose if you wanted to, and you just go find the file. But just when you load the bostonhousing.csv, make sure you have it in the right format in your working directory. And if you don't remember how to find your working directory, it's get wd open paren close paren, and that'll give you your working directory. Make sure your file is in that working directory. Otherwise, you can do the file.choose function, and you can go search for it. All right, so anyway, we've loaded up the data. We're going to look at the plot of age, that's the average age of houses in a particular neighborhood, against NOx, which is the average levels of nitric oxide. And so does there appear to be a relationship? So we'll plot that out. We're then going to build a model, a predictive model, to predict NOx based on age. Okay, so age is our input variable, NOx is our output variable. Okay, LM is the function in R for doing linear modeling. So you've got a setting. This is formula. What is our formula? Formula is basically, what are you doing? What are you doing in linear modeling? And the reason why we have to do that is because linear modeling in statistics is used for many, many, many things. And just using a single variable prediction of a linear model is just only one way that we would use a linear modeling function in R. So we're just basically using the formula parameter to just say, this is what we're doing. We're comparing NOx to age. And we're going to go ahead and then specify the data set we're using. The data set we're using is housing.df, which is the data frame that you created up here. Okay. Now that we have slope and intercept, so it's going to give us, that's what it's output. It's going to output slope and intercept. And once we have that, then we can start using that to actually calculate predicted values. So we're going to create a new variable in our data frame, housing.df. Right now it has 13 or 14 fields. We're going to create a new field called predictive value. This is one of the cool things about R, is that you just create it once and it populates the entire column, all 506 rows for you. So we're going to say that our intercept is going to be added to our age. That's how we isolate the age variable in the housing.df data frame times our slope. And even though we're not saying do it for row 1 through row 506 or anything like that, you just have to say, take this variable, and for every possible combination that is populated in the data file, run this function on it and create that variable for me. And it's pretty fast and pretty clean. And we can go through then and view our housing data frame. We see we got a new field in the data frame, and it's containing the actual predicted value. All right, that's great. So, but how good were we? How good was our value? So we're going to go ahead and calculate also an error value. So how far is our predicted value away from our actual value? We'll do the same kind of thing. We're going to create a new variable called error. It's going to be housing.df. The variable name is error, and it's going to be set equal to housing housing.df predicted value minus housing.df NOx. Our predicted value was what we predicted out of our linear model. Our NOx is our actual value. And that's going to give us 506 different error values, and we'll be able to compare those to the actual real values. So then we can go ahead and take a look at the file and see what that error it looks like. All right, so now that we've gone through it in painful detail, let's actually run it. So first thing we're going to do is, I'll go up here and I'm going to position my cursor and run one step at a time. This is run the whatever line or selection. If I selected the whole thing, it could run the whole thing all at once, but I want to walk through it one line at a time. There we are. Housing file is loaded into the data frame housing.df. Okay. And the next thing I want to do is I want to plot it. Let's plot it. What does it look like? Does it look like there is a relationship? It looks a little bit like there's a relationship. We're not calculating a correlation coefficient, but we could. And we'd probably see a positive, moderate positive correlation. So that at least gives us some sort of an idea that there is a relationship between these two variables. And one might be able to be a decent predictor of the other, but we're probably going to have quite a bit of error in our model. Let's go ahead and close that out. Go back to our script, start running lines one at a time again. Okay, the first thing we're going to do now is we're going to say, okay, build me a model. Well, it doesn't really build anything. What it does is it gives me two values. It gives me my intercept value and it gives me my slope value. And those are basically my model, right? Because then I use those to build the model myself. There is my model. Now, I went ahead and popped these values in already, but you could go ahead and, when you want to create your new predicted value variable in your data frame, you could go ahead and do this on your own. So this becomes your model. Housing.df predicted value. That's my predicted value for my NOx. I could have probably been a little more descriptive that it was for NOx. Equals 0.348204 plus whatever the average age is times 0.003011. For every one of my 506 rows, it will create that value for me. So let's go ahead and do that. Variable is created. Let's take a look at it. View. Okay, let's expand this view out. There's my predicted value. So my predicted value is set here. That's 0.54 for the first row, 0.544212. And my NOx is 0.5380. We're pretty close, right? But if you look at some of these, they're not so close. Like this one here, 0.4690 is comparing to 0.585779. That seems like it's a little further off. It's going to be kind of tough to sort of eyeball all 506 rows, and we couldn't really do much with actual the difference until we actually calculate the difference. So let's go back. We'll close out the view here. And we're going to go back to our script. And now we're going to actually create that error value. So we'll go through. Error is going to be set equal to the difference between my predicted value and my actual value. And it's populated that field. And I can come down here and I can say, all right, let's take a look at what's in there. And now we have the error value. So what we can do now is a number of different numerical things, such as squaring the error to get rid of the negatives, or taking the absolute value of the error to get rid of the negatives, and taking an average, or we can take a total, or various things that we could do to actually calculate what the error in our model is in a meaningful way. But this is kind of what I'm going to have you do this week when you do your assignment. Is you're going to use the Boston data set, but what I'm going to have you do is basically build this script with two different variables. So we'll go back to the PowerPoint. Okay. For this week, we're going to load up the Boston housing data set. You've already done that. You know how to do that. Put it into a data frame called housing.df. Let's look at the variables median value and rooms. And what I'm trying to figure out is if there is a way for me to use the number of rooms in a house to predict what the median value would be. So we have median value, we have average number of rooms for houses in that neighborhood. Is there a relationship between these? So I've kind of handing you everything right here, and I want you to go ahead and put together a script. We didn't calculate correlation, but you can calculate correlation between housing DF median value and housing DF rooms. You can draft a plot using ggplot. Now I'm going to actually have you use ggplot, and I want you to remember that, because it will show you a trend line. I want you to remember that you have to use the library ggplot2 to load those functions. We downloaded that package last time in order to be able to do some of the visualizations that we did last week. So you should still have that on your computer unless you've changed computers. And if you've changed computers, you're going to have to download the package to your new computer. But anyway, you go ahead and do library ggplot in order to be able to pull up those functions, and then do a ggplot. Your data source is housing.df, your aesthetic values, your x variable and y variables are there. You're going to do a genome point, which is basically a scatter plot. You're going to have color, green, alpha is 0.3, which is your translucency, and you're going to add a smoothing line, and the method you're going to add is going to be linear modeling. Okay. Then you're going to build a linear model for those two variables, just in the way I've showed you here. Tell me what the slope and intercept are. Can you calculate the predicted value? So we did that, housing.predicted value, intercept plus RM times slope. Creates and populates the predicted value column, and then can you calculate the error between the actuals and the predicted? Go ahead and do that. And then I'm going to have you do one more thing that I didn't show you how to do, and that you'll be able to do it, I think, fine, is just use the sum function. You can use sum, and then it's basically open paren, and then you're going to do housing.df $error. Close paren, and that will give you that value. What I want you to do is do some of this work and then save it to a Word file. You can copy and paste a lot of this stuff into a Word file. And if you have any questions about how to do that, just hit me up with an email. But it's pretty simple to go ahead and drop that stuff into a Word file. And then when you do that, you will turn in that Word file. That will be your assignment for this week. Okay, if you have any questions, let me know, and I will look forward to seeing what you come up with.